There we go. Okay, it's good. They all look different. So let's see those. Okay. You're going to have one come down. Oh, well, that is very long. That is not going to help.
Weird perspective.
Yeah. We didn't do that. Sorry. Just give me this one. Did it? Yep. Nope. It actually is that. Okay. So let's just. And we'll just make it look as wonky as we have to. Okay, so we have one going down that hydrogen. And so that sigma V, of course, will then cause the other two hydrogens on the other side to switch places. And so each hydrogen on the ammonia is going to give a sigma V like this. There are no sigma V primes because all of these sigma Vs are identical. They're identical. But let's look at the chloroammonia. So first off, we see that we lose the C3. We don't even really have a C2, so we're losing our rotation axes. And we only have one sigma V. Which is going to go right between those two. So it's going to go between. It's going to go up. The chlorine nitrogen bond is going to be in front of that one, behind the other hydrogen, and so it splits those two hydrogens in two. So this is really just an exercise to start thinking about what you lose as you start replacing atoms in a molecule. You can see you end up losing a lot of symmetry.
Yeah.
Okay. So let's talk about. So look at this. What kind of symmetry elements do you see in this? It's more complex. These are the kinds of molecules you'll see inside crystals.
I guess if I went like kind of through is that an osmate? It says the one in the middle.
Tricarbonyl trichloroosmate. So
like if the oxygens were on top and the chlorines were on bottom.
Yeah. So well, yeah. So first, I don't want to give it away. There is an axis of rotation, and it's really hard to see.
Yeah, is it right down?
So are you thinking, like, let's say, so it's kind of coming out at you like this.
Yeah.
And so then what it will do is as it rotates, it'll rotate this carbonyl group into that one, kind of like that. The chlorines will rotate into each other. Can you see that?
Yeah.
What kind of axis is that?
C3.
C3. This is one of the ones on Otterbein, so I'm trying to pick those so you can go look at them.
Yeah.
What about reflection planes?
I mean, if we kind of like cut down the middle, like, you know what I'm saying, like kind of like parallel with the screen, ish, and then.
Well, so the way we want to think about this is we need to cut down we need to cut through the center to from a chlorine to a carbonyl. Is that what you're thinking? So let's look at this. So what if I cut
like along the part where it does kind of like a square, like that's a plane. You know what I'm saying?
This one's difficult. This
I don't
one's
know.
So
I don't know how to explain it either.
and let me show you what I'm looking at here. So what if I did, trying to figure out the best way to draw this. Okay, so I'm gonna go up, hide. So they start to get a match. Okay, so do you kind of see that plane along that from that chlorine to the carbonyl?
Yes.
So so what kind of reflection are you going to get?
Wait. Let me look at my things again. I guess that one is that sigma D? No, that's sigma V, right?
Yes. So what you're going to get is that's going to go to there. That one will go there. This chlorine will go down here. This one will come up here. Okay. And so then you're going to have those reflection planes along each bond that'll do that. So to kind of look at it here, we have 3 of our reflection planes. And so we have 3 sigma V's. They're all equivalent. Then you see the C3 axis. Okay, so are any of those the ones you were thinking about?
I think so. I mean, I like to think so.
I wanted to put a more complex one on here to start giving you this experience of looking at molecules that are going to be something you'll encounter more regularly, because life is rarely as easy as a homonuclear diatomic. But yeah, here, this one, and this one is really hard to look at. If you're just looking at it here, you're like, where will those go?
Yeah.
Well, so if you go along these carbonyl to chlorine, well, not one bond, but directions, the planes are going to have to lay in a place where carbonyl is going to reflect into carbonyl and chlorine is going to reflect into chlorine. Any other kind of reflection would make a different molecule.
Right.
Okay. And now a symmetry element we haven't covered yet, improper rotations. They're denoted with an S sub n. And later on, you're going to see an S sub 2n. And so always remember, whatever that subscript is, it's 360 divided by that subscript. Okay. So for example, an S3 is 360 divided by 3. So each rotation is 120 degrees. But to get the exact same molecule, you have to rotate, then reflect through the plane. Okay. Or it's a way to get the same molecule. So again, if I rotated this, I could just do a C3. That'd give me the same molecule. And there is, in fact, a C3 that's incident with that S3. However, if I do the S3 where I rotate the 120 degrees and then reflect top to bottom, bottom to top, I'll end up getting the exact same molecule again. So these are called improper rotations. They're a rotation plus a reflection. So let's think about the symmetry elements of, so here we have a trigonal bipyramidal molecule. Okay, so let's look for some symmetry elements. What do you see?
I mean the C3 axis.
Mm-hmm.
And then you can put a plane down each of those bonds. For sure. And I mean you can put a
Mm-hmm. Do you see any more rotation axes?
C2 down each of those?
Yes, you have a C2 down each bond. So again, remember our terms, these are our radial ligands.
Radial ligands.
And the up and down are your axials. So we have our C2s there. All right, now, do you see a sigma H? Horizontal.
Yes, just like along those three radial ligands.
Yep, kind of just right around the center there. Oh boy, I am so bad at drawing. Ow. Does that every day. Good enough. There's our sigma H, which is good because that means you recognize that C3 is the principal axis. What about sigma V's?
Could you get three, like going down each of the?
Yep, going down each one of the bonds, you can get a sigma V. Okay, and so then you'll have three of those. Because you have three equivalent bonds you can do that with. Do you see any other symmetry elements?
Not really. I guess I'm not seeing.
Let's take a look. Well, we forgot. Of course, if we have the C3, and we've already been talking about this, the C3, we're also going to have an S3 axis. So you got all the planes and the rotations that we talked about. So, of course, here you see your C3 and your three C2s. You see the sigma H that reflects the axial positions into each other. You see the S3, which will rotate around the C3 and then reflect across the sigma H. And then you see your three sigma Vs.
So when you say S3, it just means that you have both the.
Yeah, so your S3 will be a combination of your C3 and your sigma H. So the way we represent that is your S3 will be a C3 and your sigma H.
Is that a cross product? What's going on?
Right now, just think of it as a multiplication. Let's say you take more of this molecular group theory in graduate school, you're going to get to matrix products. So inner products, outer products, stuff like that. So right now we're just thinking of it as a combination of the C3 and the sigma H symmetry elements.
Let's see.
How about we do something with intermediate difficulty? Now that one we just did was a little bit intermediate, but let's do it again. Talk to me about the symmetry elements that you see.
Okay, I guess I could put one right down the middle that's like a C2.
Yep. Because this one, what is this? This is so. Okay, first off, this is a D2D point group, and this is cyclooctatetraene. Cycloocta, and do you recognize the configuration?
It's like the boat.
It's a boat.
Okay, it's a boat.
So cyclo, it's a ring. So the octo, there's 8 carbons. Tetraene, what does that mean?
You have 4 alkenes.
Yeah, 4 double bonds. So double bond, double bond, double bond, and there's one right in there.
Yeah.
So here are 4 double bonds. And yes, we have a C2 right around the middle. There are 2 other C2s. Can you see them?
C2, like perpendicular to that.
Mm-hmm.
Can you go both directions? Or is there 2 perpendicular to it?
And so think about it. As you rotate, you want all of these atoms to kind of do a flip and end up right back where they are.
So yeah, could I go down those 2 double bonds kind of?
Close. Try to imagine this. So what if I did?
Oh, huh.
So and it's actually really the axis is going like through.
Yeah.
But yeah, so they have one on each side, which means then from over here to over here.
Yeah.
So this is one of the ones I suggest you go to the websites and take a look at. In fact, I wonder if we could do that. Again, not something we'd be able to see on Zoom, but we're going to use Otterbein. That's why these are such good study resources. Trying to draw these and imagine them,
yeah,
it's difficult. Come on, Internet, I believe in you. Okay, this is the D2D. Here we go. So here's our molecule. Okay, so let's open these up. These. So take a look here. Okay, you see that?
Yeah.
The reason it does this is watch what it does. So that's why it's there. And so this one's a little intermediate. That's kind of hard to see there.
Yeah.
It's nice to be able to rotate it because then I can put the other one in.
I see. It makes like a little figure 8 kind of shape.
Uh-huh. So yeah. Oh, I'm pushing the button. That's fine. Keeping those. So there's that one. There's that one. So again, this is why the practice is needed.
Yeah.
Okay, so let's go back. Now, those are our rotation axes. Do you see any versions of a sigma V?
Could I go that way? Like cut down the way? Yeah, can't I just go that way?
Yeah, so
and you can do another one perpendicular to it.
Mm-hmm. So let's see, what can I do here? I try to draw this, but then we'll go over it. I can go this way. First one's a little long, but whatever. So then if we look, that sigma V cuts right between two C2 primes. So that makes it a what?
Sigma V.
Not a sigma V
Wait,
prime.
sigma, what's the other one?
It separates those two.
Sigma D?
Sigma D.
Okay.
And so then the other one you talked about would be a sigma D as well. So it would cut the other way. So it cuts between those two C2s on the other side. So we have two sigma Ds. Now, what about an improper rotation? And what would it be? An S what? This one's hard.
Yeah.
So let me go ahead and eliminate these so you can kind of see things more clearly.
Does an S have to be like perpendicular to the plane it's with?
No, usually an S is going to share the same rotation axis as the primary axis, but it doesn't have to be the same number, the principal axis. But so think about this: if I rotated it a little bit and then reflected through a sigma H, I get the exact same molecule. And keep in mind, for a boat, when you reflect, that means the down part of the boat is going to become the up part of the boat, and the up part of the boat will become the down part of the boat.
So would it be like an S4?
It is. It's an S4. Because if I rotate it 90 degrees, and it's easier to see down here. If I rotate it 90 degrees, and then I reflect, so there you see your C2s, you see your sigma Ds. So let's take a look at how this S4 works, okay? Okay, so there it is. And so the 4 means it's going to rotate 90 degrees. So like that, and then it's going to flip. Yep.
What is the inverse?
So if you see a -1 on a symmetry element, it just means go the other way.
Oh, okay.
So one of them is clockwise, one's counterclockwise.
I see.
So, but yeah, this will rotate 90 degrees, and the up becomes the down becomes the up, and you get the same molecule back.
I see. Cool.
But you got them all. So that's all righty. Now let's talk about successive operations. Okay. So one of the things I want you to keep in mind is when you're looking at point groups and eventually character tables, there's going to be symmetry operations that are not represented. That's because they're only going to represent unique symmetry operations. Okay. So let's look at successive operations. So here's our cyclobutadiene anion, and we know that we have a C4 right there, okay? So what we mean by successive is then, so if we start by saying, what, that's not showing up very well, is 1, 2, 3, 4, okay? And I start rotating these. If I rotate once through the C4, that's going to rotate everything to 1, 2, 3, 4. Okay. So I rotated once. Now, but I have a number of operations. I have a C4. I have a C24. What do you think a C24 means?
It's the second rotation.
So yeah, what that means is so I can go all the way up to a C44. Okay. C34. C44. Now, out of these, which ones would you say are unique? Which ones would be represented? Because keep in mind, we also have lower order axes in here. So that C4 shares the same space as a C2, and then you have some C2 primes and some C2 double primes.
I mean, I'm tempted to say they're all exactly the same, but
So each one of those is a C4 90-degree rotation, but one of the unique elements is going to be a C2. So this is a hint. The C24 is not one you'd see represented because the C24 equals the C2. Because that if you do two 90-degree rotations, it's the same thing as a 180-degree rotation, and the C2 is already represented, so I'm not going to represent it twice. This is a whole new, and this is one of those concepts that as we practice it, you'll get better at it. It's kind of like everything. Oh, okay, I need to look for unique elements.
So okay.
And what's the other one we would represent?
C4.
C44, because C44 is, do you remember what E is?
That's where it has only one, right?
It's identity.
Yeah. Oh, that's the identity?
Mm-hmm.
Oh my gosh.
I told you we're using E for a number of things. It's a doubly degenerate symmetry, or it's identity. So we wouldn't represent C24 or C44 because they're already represented as unique elements in C2 and E. Okay. The others we would. The C4 is unique, the C34 is unique. So let's kind of take a look at this. So there you see that the C4 and the C2 share a similar position. And down there you can see what they all equal. And so the ones that would be represented are that one, that one, that one, and that one, because those are all unique. And then, of course, just like I showed you above, your S4 is actually considered, your S's are actually considered successive operations. Your C4 with your sigma H then gives you an S4. So those are also considered successive operations. And there you can see the S4. We rotate 90 degrees, and then we can, but also, I mean, this would also have an S2. So you can start to see that.
Okay. Okay. So this is the thing that you're talking about. This is why they're stacked. This is why you have C2 and C4.
Mm-hmm.
Okay. Okay.
So a C2 is going to be seen as a unique element. A C24 is not, because it's the same thing as a C2.
Okay. Okay.
So you have your principal axis, then you want to look for lower order axes. Your lower order axes will be unique, but any successive operation of the higher order axis that matches the lower order axis is not considered unique. All right, let's start into point groups. There's a list in your textbook, so I'm kind of taking these one at a time and giving you an example of what they mean. Your CS, so we're starting with the very low symmetry, okay? So your CS point group, it's represented by an E and one sigma plane. And this one we really just call a sigma. There's not an axis of rotation that we can base it off of. So it's just a single reflection plane. Your next point group, and so here's the first time we really looked at this. Your CI point group. And every single point group tells you the symmetry of and it's groups of molecules. So your CI is E and an inversion center. That's why the subscript is I. Let's look at the inversion center. Do you remember what that means?
It's like if you turned it inside out.
Every single atom on there will reflect through there. So let's like if I take this carbon, it reflects this way. It ends up there. Okay. This hydrogen reflects that way. Ends up there. The chlorine is going to reflect into the inversion center. No, that's the bromine. Anyway, I'm trying to keep my standardized color straight. It ends up there. The chlorines do the same thing. Okay, this is what an inversion center is. Every single atom will reflect through there and end up in the counter position. All right, let's start talking about our CNs. Those are represented by E in identity, so they're all going to have E. Because you can always say a molecule is a molecule. One principal in-fold rotation axis. That's the primary way to look at these. I wanted to put this one on here because I want to see if you can see that, why that's a C3.
Because the little the phenols rotate.
They're going to rotate into each other's positions. You get the exact same and indistinguishable representation. So this is a C3 group. Other CNs, you've seen C4s, you've seen C5s, C6s, C2s. So C sub n, it's going to be represented by a principal axis that represents the point group.
Okay. But that one doesn't have any planes.
Nope.
No planes at all. Okay.
Nope. If you try to put any planes in there, it's going to get a little wonky.
Yeah.
So let's try and take a look at that. Let's go to our CN point. So now you can see these are all point groups. So which one? Yes, that one. Now it has a C3 too. So it can do that. So I'll write that on here. It has our C2-3, however you want to say that. But it can reflect or rotate once. Or it could do a two-fold rotation. Then a C3-3 is just the E, so it wouldn't represent it. But yeah, no sigmas. I love these names. Lambda, cis, cola.
Yeah.
You'll get used to that as time goes on. But okay. So let's look at this bad boy right here. And as we go through, I want to start introducing you to terminology as well.
Yeah, what does the new mean?
The eta. So that's an eta.
Eta? Okay, eta.
That is hapacity. So it is a 5 haptic molecule. So that indicates that all 5 contiguous phosphorus atoms in the phosphorus ring on the top are simultaneously bonded to a central atom. So hapacity will be a new idea for you to get used to. And so there's different ways to write this. You see that iron and then the Me. It looks like they represented that as an element, doesn't it?
Yeah.
What do you think Me actually means?
Methyl groups.
Methyl groups. So we're going to start getting used to the shorthand here. Okay. Your CP, of course, is your pentyl methyl cyclopentadienol.
And that's the orange thing on top, or is that the?
That's the carbon on the bottom.
That's the bottom.
Mm-hmm.
Okay.
So let's see, pentamethyl. Can you see that?
Yeah.
So your 5 methyl groups around the ring. Cyclopentadienol. So that'd be that 5-membered carbon ring in the center, and then they're all. So of course, then it's also a 5 haptic part of the molecule, because you see how they're all simultaneously bonded to the iron in the center. The iron is right there, either phosphorus. So the formula there are identical. It's just different ways to represent it. Yeah, I really wanted you to see hapticity.
Yeah.
You've probably never seen etas before.
Eta.
And you start getting used to shorthands. So cyclopentaphosphorus was it. But yeah, the pentamethyl cyclopentadienol. The chemists, we don't like to say that all the time, so we have abbreviations. But the abbreviations will stay consistent. Okay. So I wanted you to start seeing, for example, that the Me, that's not an atom. That's a methyl group.
Yeah.
Now, what symmetry elements do you see?
Would it be C5?
Okay, so.
Like if I do one right down the middle?
Yep, you have a C5.
I don't see any else, maybe?
Let's see.
Do the bonds of those methyl groups and are those phosphoruses, do those line up? Like, are they perfectly aligned with each other?
I think they are, but that doesn't really matter for this one.
Okay.
So let's think about your unique elements. You have a C5. What other unique elements do you think? Let's just focus on the rotations. You have 4 unique elements.
4?
Uh-huh.
Oh my. Okay, so you can do the C25,
C25, that's another one.
C35, and C45.
Mm-hmm. Those are your unique elements. This is a C5 point group.
Okay.
So if we go back up to our CN, E and a principal infold rotation axis. And so that's all we have here.
Okay.
Mm-hmm.
Okay.
Just a big molecule with some new things you haven't seen name-wise and idea-wise. And you can see now the I lost the word. The successive operations. I want to try to reuse the right terminology. You can see the successive operations. You can see that C55 is not going to be unique because that's identity.
Yeah.
So you have those 4 unique elements.
So is just the normal C5 also E? Or is that something?
No, just the regular C5.
Yeah.
So the C5, no, it would change it by taking that to there.
Oh, so that's C15. We just don't draw the 1.
Right. Yeah, that's C15. That to there, that to there. So yeah, that's just a single C5 rotation.
And identity is just assumed. You don't need to.
Yeah, so identity is like that. You just don't do anything to it. There.
It's that. Yeah. Okay.
Yeah. So every molecule has identity. Now we'll go back to one that's a little easier. A CNV. So what we have here is a C3V point group molecule. You have identity, of course, one principal infold rotation axis and N sigma V planes. So where's the rotation axis?
Down the oxygen.
Yeah, down the oxygen. That's the only place we can rotate at the same. Just rotate those chlorines into each other. And that's a C3 axis. And then you have this combination of vertical planes, which is going to get us to the C3V point group. Again, I'm going to give you a flow chart of how to do this. I just want you to start kind of envisioning the elements of each point group before we do. So I put one of the sigma V's on here. How many are there?
3.
3. And the sigma V's are going to go down each chlorine like that. Each chlorine phosphorus bond. What about a CNH point group? I use this one because it has another naming convention.
This one hurts to look at.
It does. So you have a principal infold axis, a sigma H, an improper rotation axis, which is coincident with the CN axis. For N of 2, 4, and 6, there is an inversion center. This is a C6H molecule, so we know there's an inversion center too. So hexakis methyl nitrobenzene. So let's just look at the methyl nitro part of that. What is that representing in this molecule?
That's the blue ones. Right?
Yep. So I think it's more like dimethyl nitro, but you see the nitrogens with the dimethyl with the 2 methyl groups on them. That is your Me2N. Those are your Me2N groups. Benzene, of course, we see that in the middle.
Right.
Hexakis. This is a new term for you. That's an IUPAC naming convention indicating that 6 complex ligands are bound to the molecule. Mm. So do you remember when we were doing general naming and we had hexa met 6?
Yeah.
So that we usually use hexa for more simple molecules. However, you could use hexakis for all molecules and be right.
Mm. Okay.
But in this case, hexa just really doesn't cover it. We need to use the full Greek hexakis because we're representing these really complex dimethyl nitro ligands.
So it's just kind of saying like there's one on each one of the benzene ring.
Mm-hmm.
Okay.
Yep. So there's 6 of them.
I get it.
6 of those ligands. So again, if you see the word the first time, you're like, holy crap, it's not that complicated of a definition. So this one here has all of those so of course,
That's C6.
and also on there, you're going to have an S6, because then you could rotate and thunk.
Yeah.
The inversion center is a little more difficult, but let's just let's do.
I see it though.
Yeah, that. So this up molecule, this up methyl here, will go and become the down methyl there. This down methyl here will go become the up methyl there. So on and so forth.
Yeah.
And so then, like just around the benzene ring, that carbon will become that carbon, so on and so forth. So you can start to get an idea of the inversion center. The S4 rotation, of course, is going to have a sigma H plane in there. And that's really going to be all, as your sigma H is going to go right around the center, like we've been seeing all of the S's. Let's take a look at this on Otterbein so you can see what I'm talking about. C and H. Here we go. Okay, here it is.
Okay.
So now our C6 rotation. Now, of course, we have, again, we have our unique elements. So, I'll write this. So your C26 equals your C3, okay? Your C36 equals C2. Then, what's fun, C46 is actually going to be your unique C32, okay? Then you have your C56. But again, and then you see the unique S rotations and whatnot. But let's look at an S rotation. Inversion.
Okay.
Here we go. Oh, don't do that. Oh, let's do an S3, see what it looks like.
Yeah.
Yep, see? And so it's hard to see, but they really do just reflect across that sigma H plane right into each other. So there it is. There's your S axis. And of course, this is your C6H. Oh, here's your S6. It just rotates once and then reflects.
Mm.
So again, and then your sigma H. There it is. So harder to see on a molecule like this, but again, after you actually see the symmetry elements placed, you can pick them out better.
Sure.
And I hope I'm not boring you too much with all of the examples.
No, it's good. I like seeing it on the playback.
Yeah.
It makes more sense.
And so, but the more of these you look at, the more it's going to make sense to you once you start placing. Because here's the thing, to place these into point groups, once I give you the flow chart, you're going to have to be able to envision all of these.
Yeah.
Because you're not going to be told that this is a C6H.
Yeah.
You're going to have to go through the flow chart, figure it out. You're going to be able to envision all of these symmetry elements to get it into the proper point group.
Okay, cool.
So we'll pick this up again on Monday, and we'll finish this out and take a look at some more point groups and their elements, and then talk about the flow chart and some group theory.
Cool. Yay. Do we have a quiz for this class next week?
Yes.
All right. Hopefully for real this time.